because it's a hyperbolic toroautomorphism, if I take any region U with measure less than 1, and I take the measure of this, in the limit, this is going to go to 0 as n goes to infinity. So I know I'm going to have a set of measures 0. But that enough is not enough. That could be all the rational numbers as a set of measures 0. So I want to use the fact that the area is this is going to 0, but I want to make sure it stays a polygon, no matter how many times we intersect it with itself. And what we can prove, when you take one of these convex sets, okay, and then you apply the automorphism to it, and you get something like this, okay? It might be that it breaks up into 2 pieces, but if it doesn't, on the first sort of twist, if it doesn't, and we get something convex, then I'm guaranteed that every further intersection is going to stay convex, one connected component. So we can guarantee it won't break into pieces. And in fact, between that being true and the area of the measure going to 0, we know it's going to go to a line. And we can say exactly what line is in there. Okay? So we can handle that. And we had an application to number theory that came out of this. That was originally where it came from. So then I want to talk a little bit about some further work to kind of wrap up. So I know everything here is below a half, but I don't really know what to say about this. For example, is this dense? Are there finitely many points up here, or is this going to get filled in? Are they going to have dense? Are there going to be infinitely many, or even dense regions? Are these gaps real gaps, or will things fill in here? Is this a real gap? Okay. So we can ask these questions, and so what happens is, for example, if I want to test whether this is 1/8, if there's anything between here and here, so I could take my so I can take my open region as open region here. So 1/8, 7/8. And again, this will be the region U, and we look at. I want to know what this looks like, and eventually, because we know that there's 4 points here that definitely will stay in here. Then we're going to get, turns out we're going to get something fairly complicated, because we don't just have 4 regions here, but we actually have, you'll have 4 copies of this. You'll have something that looks like this, and something that looks like that, and then on the next iteration, one of these, it'll intersect and go away, but this itself splits into 2 pieces, right? And so on. So if you want to look at it like a graph, you have like 2 nodes, and in the next iteration we've got 2 more. This one goes away, and then this one, and so forth. So the only one that's left in the limit is this here. So in order we can kind of guess what we think is in there, and probably is not too hard to prove in this special case that, in fact, there is nothing in here, but this is truly a gap. But it'd be nice to actually say something a bit more general about how to handle when we have a lot of different pieces interacting with each other. Because this is where some more experimentation should come in, because we can see a lot of strange phenomena. For example, do we get just a finite number of regions, and does it stabilize? Or do we break up into a lot of pieces? So, for example, if we extend further and we try to see what's going on down here, so I make my region a little bit bigger, I don't know, we'll call it 1/10 or something. Okay. Then it breaks up into many pieces, and not a stable number seem to be growing to infinity. So at every iteration they get larger and larger. So we get something that looks like this. And well, the reason why they aren't stretched out all skinny, because as I realized as things got more complicated, it was hard to look at that. So it actually makes sense to look symmetrically. This is just as good to work with if there's a finite orbit that's in there. It doesn't matter which direction we apply the automorphism. And the advantage of this is we get regions like this intersected with regions like this. So we have little squares, and it's a little easier on the eyes to understand what's going on. So then the question is, so now we got some more general geometric problem is, so okay, when we have a region of the torus, and we apply a hyperbolic toroidal automorphism, like this very basic one, the Fibonacci one, sometimes called the hat map, and we intersect with itself at its inverse, and we take the rational points, what do we get? So this keeps growing into, and it seems to be growing infinitely many points. It seems to be, I believe they're points and not lines. I think they would have to be given what's going on here with the different, taking the automorphism in its inverse. But not necessarily all these are going to have rational points in them. Right? That's something we need to prove. And then what I'd like to know is then projected onto like one axis, what do we have? Do we have something that's, do we have finitely many points? Do we have a period areas which are dense, or infinitely many? Where are the accumulation points and so forth? So that's sort of where we are in the problem, and so I think we need a bit more, maybe a bit more experimentation, and it'd be nice to actually talk about, put some general structure around this problem. There's a lot of work on these kind of automorphisms, but again, mostly from looking at the irrational orbits. Looking at the rational ones is, most of the theory is fairly silent on it, so I thought this may be an interesting problem to look at. So that's all I have today. So I wrap up.
You have time for questions?
I have a question.
Yeah.
I always find Fibonacci pretty boring. Have you thought of trying this machinery on some more interesting sequences?
Well, I mean, these are for recurrent sequences. For example, we can do higher dimension. You can do higher dimension. So I had. One reason this came up is I was up visiting someone up at Amherst, and they were looking at trying to repeat this for cubic fields. And so they wanted to do it for, so we need a three-dimensional box, and even just experimenting how to keep track of it. And well, I wrote this all up in Maple, and it's got some code to like move around regions or whatever. And in 3 dimensions, it's just that much harder to. I'm not sure there's any. I mean, there's a lot of people that do computer games have all this software for intersecting polygons and so forth. That's where I got that from. It's kind of standard algorithms, but I don't know for 3-dimensional polytopes and intersecting them and then breaking them apart and moving them back onto the torus. So even knowing computationally what that looks like is a bit of a challenge.
What would the sequence be for that? It's a sequence of integers?
So that would be for any third order linear sequence. So there's something like this. I mean, what you can do, experimentally, you can easily just do this. You can go back and you can do this kind of chart, right? And that you can do. You just pick a bunch of moduli and you plug in things and you see what you get. You get a rough idea of what's going on with it. But if you want to then prove something with this idea, you need to handle kind of 3 or higher dimensional regions. So I think it's doable. But it seems like sort of the thing that should be done by a graduate student.
I was thinking more of nonlinear. I was thinking more of nonlinear recurrences.
Well, I hadn't even thought of that.
More room to have fun.
In that case, your sort of the torus isn't counting the same thing you want it to be, because when you apply maps like to a half, it'll suddenly shrink the denominator for some reason, or
I mean, I don't see any reason why you couldn't look at it. I just hadn't. I struggle with even the very basic things. I hadn't thought of it.
Another possible extension is to have C1, C2, and C3 be polynomials in X, and also still do it mod M, but then you have 6 as a polynomials. Does it make any sense?
I think it does make sense. I mean, I'm not sure how to think about it, but you know, you can experiment. I guess.
Is this work available? Is it written up?
So I can give you my slides. I have a write-up of the number theory application. I have a draft write-up on my old homepage, which I hadn't even put on archive yet. And someone found it. So never post anything unless unless you're sure that you want to have someone see it. The rule. But I'm going to try to clean things up and get them on the archive. I'm finally inspired to do that. So I will try to write this up. I can send you a copy of my draft.
Please.
I mean, it's hard to find something new with Fibonacci sequences. It is a quarterly journal, right? And they have stuff all the time. But I think this is a little different.
Another question?
Yep.
Yeah, so for Wall's conjecture, do you have a heuristic for what the likelihood of a counterexample should be?
That's a good. I mean, to find a Walsh on some prime. Yeah.
Yeah.
Like why?
Can't
Yeah, that's a
people
good question.
can't
Like
be
I didn't
right?
look into that, but why is it that people think there are infinitely many, but they haven't found any
Right,
up to
right.
10 to the 17th?
It's like the probability like one over B.
Yeah, I don't know.
Like
I was going to look into that. I haven't yet, but you kind of wonder if the heuristic might change once you got up to 10 to the 17th. But, right. I mean, it depends on, I don't know. Is it something that becomes progressively less likely as the prime gets bigger? I guess so. But how? I assume it's some pseudo-random process, and they probably did some analysis and said, well, there should be infinitely many, but depending on how quickly that probability is dropping, it's a good question. A lot of people, I think, this is something people think about. So I'm sure it's in the literature.
Oh, I have another question, sorry. You may have answered this and I missed it, but do you know of any recurrent sequences for which the spectrum is dense in a certain region?
Yeah. So the very first example, this one.
Oh, yes, right, okay.
Yeah.
Yeah.
So, in a kind of trivial way,
Right.
it is.
Okay.
So, and I guess another recent literature, I guess Sommer has had a couple papers out in the last year or two, where he's looking at a little bit different problem, but he's looking also at distribution on P, these kind of sequences. He asks a bit of a different question.
Thanks again. It's not a great to ask the questions in private. Also,